Annenberg Media.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And
metals seem to be everywhere. They form the superstructure of our cities. We can make cars, rings, and refrigerators out of them. But what do we know about metals? What is it about metals that makes them so useful and valuable? What is there about their makeup that gives metals their properties of luster, conductivity, ductility, and malleability? And where do they come from? Civilization has been shaped with metals.
I'm at Dulles International Airport near Washington. Those terminals behind me owe their existence to metals. They're built out of aluminum and steel. There is steel in the reinforced concrete in these runways. There is copper in every wire that brings electricity into those buildings. There's also metal on my body. I've got a metal belt buckle, a watch, eyeglass frames, a zipper. I'm wearing a gold ring. The airplanes behind me are built out of anything but gold, though they're pretty expensive as they are, those marvelous flying collections of metals and metal blends that are called alloys. Metal tools have shaped these airplanes, and these airplanes in turn themselves are tools for transportation. I stress tools because it is as tools and as weapons, the plowshare and the sword, that metals have shaped our civilization over thousands of years.
Metals serve as the framework of our material world. They're in our buildings, roads, and the traffic that surrounds us. Metal machines make metal products, products that we wrap in metal, ship in metal, and use every day. Even food comes sealed in metal. We use metals to generate electricity, and then we transmit it across the country in metal wires. We make crowns with them, and coins with them. Of course, it's not surprising we have found so many ways to employ metals. About 3/4 of all known chemical elements are metals. The most abundant in the Earth's crust are iron, aluminum, as well as calcium, sodium, potassium, and magnesium. There seems to have been a direct relationship between the metals we used, how we used them, and civilization. Human progress was even marked in terms of stone, bronze, and iron. As our needs become more sophisticated and our abilities to produce metals and alloys become more advanced, our uses of metals become more specialized and diverse. But what is it about metals that makes them so useful? They conduct heat and electricity, and they're malleable and ductile. They can be pounded and drawn into many shapes. These are physical properties. What chemical properties do they have? Most metals are oxidized, and in the process, they give up electrons. But some metals are more reactive than others. Some oxidize more readily.
I feel extravagant today. Let's try to burn a piece of platinum metal. So I'll light this burner. And here's my piece of platinum wire. I'll put it into the flame and watch what happens. Oh, you see that it's conducting the heat very well. In fact, it's getting red hot. But it's not oxidizing. Let me show you. I'll bring it outside, and we let it cool, again, the heat is conducted away from the metal very easily, and you see it's right back to normal. Thank goodness, huh? That's a lot of platinum. Now, we know other metals, though, oxidize readily. For instance, this rusty old screw that I have here, we formed iron oxide. Iron oxidizes. Aluminum, you might not know, oxidizes even more readily than iron. So, in the process of competition for oxygen, which would win, iron or aluminum in that process? Well, I have a little experiment that I want to show you that will exhibit that. Inside this clay flower pot, I have a mixture of aluminum powder and rust, iron oxide. And I have this magnesium strip here as a wick to initiate the reaction. Now, when we do initiate that, what we will see is that the aluminum will reduce the iron in the rust to form molten iron. And you will see a stream of molten iron come out of the bottom of that clay flower pot and be caught down in this system down in here. Now, there's a tremendous amount of heat given off there, so I'm just going to put on my face shield and get out of here, huh?
The difference in reactivity between the aluminum and the iron is accounted for by the difference in the electronic structure of the atoms.
Wow, that was quite a reaction, huh? Did you see that molten iron flowing out of there? Well, let me see if I can fish out some of the iron out of there. I've got this magnet. This is a thermite process that you just saw. That is used in welding, underwater welding, and railroaders use that for welding rails together. Oh, there's the nugget. Look at that. Now, what you have seen is that aluminum has reduced iron oxide, rust, to iron metal. To help us understand why metals have their characteristic properties, we're going to have to look at their molecular makeup. Let's imagine now that these balls are metal atoms. I've got two different colors now so that you can see them. Metals certainly have all the same color. How would we stack them? Well, we would put the balls into the notches provided now by that lower layer. And this type of stacking is what we call the close pack sort of structure. All the balls fitting into the notches of the lower layer. Now, this type of structuring is what allows metals to act as they do.
Metals are crystalline solids. In most cases, they have a fairly simple symmetrical structure of close-packed atoms. Notice here, the second layer is formed by atoms resting in the depressions between the atoms of the first layer. In this case, the third layer is stacked exactly above the first. When a large number of metal atoms come together, forming a crystal, an interesting phenomenon occurs. When a valence electron from one atom feels the force field of the neighboring atoms, it leaves the original atom, briefly attaching to the other. It then moves to another, and yet another. We say these electrons are delocalized. They are free to wander throughout the entire metal crystal. We can picture the metal structure as a close-packed arrangement of positive metal ions immersed in a sea of negative electrons. When we apply an external electrical field, the delocalized electrons begin to drift from the negative to the positive side of the field. This is how they carry electrical current through the metal. It's this freedom of the electrons to move that also enables metals to conduct heat and reflect light. But why are metals malleable and ductile? The answer there, too, is found in the metal's structure. Because the electrons are free to move, the metal ions can slip over one another, as if riding on a cushion of electrons. This slippage is facilitated by the presence of imperfections in the arrangement of the atoms. But how exactly do we get metals from the Earth? And what has to be done so we can put them to use? Iron is one of the world's most well-known and useful metals. The most common way of obtaining iron from the Earth is open-pit mining, like this in Australia. If it is commercially feasible to extract the metal from the mineral mixture, we call that mixture an ore. Most iron ores are oxides, but occasionally iron is found as a sulfide mixed with other rocks. When a low-grade ore is mined, it must be physically separated from the other rocks and dirt. Only then is it ready to be shipped to a smelting plant where the metal will be extracted from its ore.
Different metals come from different ores, but heat alone may not be enough to obtain metals from their ores. What else needs to be done?
We're going to have to add a reducing agent. And a common one that is used in this type of process is hydrogen gas. So I'm going to put some of the iron oxide, the hematite, in this boat. This is a little combustion boat. Get some of it in there. And I want to do another experiment while we're doing this one and see if it will work. I'm going to take some aluminum oxide and put it into this other boat here. Okay, you'll get enough of that powder in there. And what we'll do then is put these boats inside this combustion tube. All right, here's the hematite. Put the hematite in there. Push it down the tube a little bit, hopefully not turning it over. There we go. Okay, and this is the aluminum oxide. We'll put it in there. And what we're going to do now is pass hydrogen gas over there and see if it's possible now to get the metal from the oxide. We'll see what happens. Close it up. And then I'll put some hydrogen gas from this source over here, run it through here and pass it over the metals. We'll turn that on. And now what we need to do, now we got hydrogen passing over there, we need to heat this. Now this probably will take some time, so I'm going to heat it. Well, we've heated it for quite a while, passing hydrogen over there all the time. Let's see what happened. Now, I hope it's cool enough to handle. Let me take the cork out and see if I can grab those little boats out of there. The first one now that I'm going to grab is aluminum oxide. It doesn't look much different than what it did originally. And then the second one now is the hematite. Let's see what it looks like. I'll grab a hold of it. Oh, it looks quite different. Let's look at that one. So what we can do, we can pass a barb magnet, I have a small barb magnet here, over that hematite, and if it did indeed reduce the iron, we should see some of that iron. Look at that. The iron was picked up right by the magnet.
Iron is most commonly produced in a blast furnace like this. The furnaces are huge, 30 meters tall and 10 meters wide at the base. Iron ore, coke, and limestone, calcium carbonate, are loaded into the top of the furnace. Then hot air, about 600 degrees Celsius, is forced through. As the carbon in the coke burns, the temperature rises even higher. Carbon monoxide produced by the burning coke moves up within the furnace, and both it and the carbon react with the iron oxides, reducing them to metallic iron. At these temperatures, iron melts and sinks to the bottom of the furnace. Meanwhile, the limestone decomposes to form calcium oxide, lime, which then reacts with the silicates or sand that might have been in the ore. The calcium silicate which forms floats to the surface. But in the case of aluminum oxide, this type of reduction simply doesn't work. Aluminum couldn't be obtained in the laboratory because hydrogen just isn't a strong enough reducing agent. Electrical energy, a lot of it, is needed. The process is called electrolytic reduction and is barely over 100 years old. Charles Martin Hall, an Oberlin College graduate fresh out of school, invented the process in 1889. Prior to that, aluminum was so rare, it was the metal of kings and queens. Aluminum oxide is dissolved in a molten aluminum salt. The melt is then jolted with 130,000 amps of electrical current, reducing the aluminum oxide to metallic aluminum. The power requirements are enormous. One aluminum plant in Frederick, Maryland, uses nearly a fifth of the total output of the nearby Potomac Edison Electric Company. Once aluminum has been purified, though, it takes only 5% of that initial energy to recycle it, making aluminum more economical.
We're in the National Building Museum in Washington. You can hear the sounds of renovation around me. That sculpture is actually a sheet metal exhibit celebrating the wonderful properties of these materials, which we use in our furnaces, in roofs, in ductwork. The sheet metals used in this exhibit include lead and tin-coated steel, zinc-coated steel, that's called galvanized steel, copper, and brass. Now, copper, this beautiful shiny copper, is a reasonably pure metal, but the others are alloys, blends of two or more metals or of a metal and a non-metal. Since the beginnings of metallurgy, one of the first chemical technologies, it became clear that when one mixed two metals, that sometimes, not always, one obtained properties, melting point, strength, that were superior to those of the components. The first such alloy, bronze, an alloy of copper and tin, was sufficiently important to have an age named after it. Soon after bronze came into use, people discovered another alloy, steel.
Steel. More than any other metal, it drives the economy of the modern world. Most commonly, steel is made by the basic oxygen process. A furnace is filled with pig iron, limestone, and scrap steel. First, the impurities are burned off with a blast of oxygen. Then, carefully measured amounts of carbon are added, producing the alloy, steel, which is harder than iron. But how does the addition of small amounts of carbon make iron stronger? When you add small amounts of carbon to iron, as little as 1 part per thousand, the carbon atom, being smaller than the iron atom, fits into the interstitial spaces of the crystal. This small change in the structure of the iron crystal makes the slipping of the iron ions more difficult. That's why steel is stronger than iron. This is Armco Steel in Baltimore. They make stainless steel here. Senior metallurgist Gerald Galizella.
We make basic alloys, probably 3 or 4 dozen, but variations on those in which we put a little pinch of this, a little pinch of that. We can make 200-300 varieties, more than Heinz ketchup. An alloy, basically some metal like base iron, to which you add some other chemical elements like chromium, aluminum, nickel, copper. Out of the periodic table, you may add a pinch of sulfur. That will give you machinability.
This is 50 tons of molten iron. A pinch of chromium could be as much as half a ton. A pinch of boron could be as little as a few pounds.
I'm still accused of being a witch doctor, so to speak, with the little pinches of this and the little pinches of that. But we do know what we're doing.
The alloy they're making here is called Nitronic 32. It's a special alloy that will be woven into wire mats and cast in concrete. The concrete slabs will then be used to line the banks of the Mississippi River to control erosion. Simple variations in composition can result in a variety of alloys. From car antennas to turbine blades, we use these alloys every day. As alloys enter the mainstream of American life, the elements needed to make them gain special importance. But the United States doesn't have the naturally rich deposits of some ores that other countries do.
Nickel primarily comes from Canada. The chromium may come from Rhodesia, Africa somewhere, or the Soviet Union in some cases.
What if, suddenly, we couldn't import the metals we need to make our alloys, the chromium or the nickel? How could we design and then substitute other alloys to manufacture the products we need? Just how dependent on these metals are we? The engines that propel this missile and the fins that guide it are made of superalloys, alloys that can withstand extreme temperatures and stress. Most commonly, they are made of iron and nickel, or iron and cobalt. Dr. Lance Davis.
The source of cobalt is outside the United States, and therefore it is considered to be a strategic material. And you get exceptionally good properties in cobalt superalloys, but one would like to be able to produce the material as inexpensively as possible and not be susceptible to loss of supply due to changes in the political climate in another country.
But the uses of superalloys isn't limited to missiles and space exploration. This 80-ton airplane is about to land, and the wheels will have to support the weight and absorb the heat generated by the brakes.
There are 3,300 airplanes like this, and each plane has an average of 10 wheels. They cost over $8,000 each, and they do wear out. Salt corrosion and stress are the two major concerns.
The particular driving force in our own interest in aluminum has to do with various types of applications where corrosion resistance and high temperature resistance could stand to be improved.
This is aluminum foil. Chemically and physically, it's very different from household foil. It's an alloy containing iron and silicon and other elements. In ordinary casting like this, the metal cools slowly and the other elements can combine, crystallizing together. Weak points would form and cracks could develop. But researchers here at Allied Signal Corporation found if they cool the molten alloy quickly, up to 100 degrees in a fraction of a second, the aluminum would solidify before the crystals could form. This created a new aluminum alloy. Its enhanced strength came from the iron, and the good heat resistance came from the silicon.
That really is the forte of the material scientist, is to try to control, to use changes in chemistry and processing to produce a material that has the unique properties that are required for a particular application. It all depends on the particular application that you have in mind and the properties that are required for that particular application. But there are many ideas and dreams that people have today which are ultimately limited by the availability of materials.
To review, metals are used to form the framework of our cities, but there are many metals with many different uses, from jewelry to steel beams. 3/4 of all known chemical elements are metals. The most abundant are iron and aluminum. Metals are malleable and ductile. They can be folded, pounded, and drawn into many shapes. And they conduct heat and electricity. These properties derive from the microstructure. At the micro level, metals are crystalline solids with a close-packed structure of atoms. Within the crystals, the valence electrons are delocalized and free to wander throughout the crystal. While all metals have many chemical and physical properties in common, they can be vastly different. So techniques for obtaining metals from their ores vary. Chemical reduction is used to obtain iron, and electrolytic reduction is needed to produce aluminum. Alloys are blends of metals and other elements which result in new materials with new properties and uses. Some countries don't have the ore deposits others do, so shortages or costs promote the development of new alloys.
It's been a long road full of art, craft, and science, from copper and bronze to a new nickel-iron superalloy. And there's more. So far, we've talked only about the mechanical properties of metals and alloys, their strength, their malleability. But there is more about metals that makes them valuable to human beings. There is their luster, think of mirrors, or magnetism, the unique features of iron as a magnet which made compasses and navigation possible, or in our century, electrical conductivity. Copper is an extraordinarily good conductor of electricity when it's fashioned into wires. At the beginning of this century, people discovered a new phenomenon in some metals and alloys. These metals conducted electricity without resistance, essentially endlessly, but they did so only at very low temperatures, where it was not useful to make any devices from them. Something changed around 1986. First one material was made, then another one. And these were high-temperature superconductors. Let me show you one of them. It has in it yttrium, a rare earth metal, that's the blue balls, barium, an alkaline earth metal, that's the white balls, our old friend copper, and ubiquitous oxygen. A real cross-section of the periodic table. This material is really a superconductor and at a high enough temperature that I think we will soon see wires and magnets fashioned from it. There are new metals and alloys with special properties still waiting to be discovered.
Annenberg Media.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And
For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.